variables today. And you all remember that a random variable is a mapping of the outcomes of a random experiment onto the real numbers, right? And so I talked about how you might define that for rolling a die or choosing a resistor, that kind of thing. And I talked about this. Now I'm going to switch to generic notation, f sub x of x. And that is called the what? In one word, it has three words in the name, but in one word we call it a probability density function, commonly called a density. And the capital F sub x of x, which is the running interval, negative infinity to x, little f sub x of alpha, d alpha, this is called a distribution. And distribution function, commonly CDF, cumulative distribution, PDF, probability density function. And capital F sub x is the probability that the random variable is less than or equal to the value lowercase x. So capital F sub x is a probability. Little f of x is d by dx of capital Fx. So that is the derivative, which means in order to get a probability from the density, you have to integrate it, right? Cumulative distribution is a probability. The density function is not a probability. And so let's talk very briefly about some common density functions. So common density functions. And there are a couple of them that you have probably heard of, and one of them I'm certain you've heard of. Let's say f sub x of x, and it is this one, which we say that this random variable. Question? Oh, you had a question?
Above the dx, what's that, Dr. Byron?
Which one?
Yeah, above the dx.
Oh, above there?
Right
there?
Yeah.
D by dx?
D by dx.
D by dx. The derivative.
Okay.
Okay, so this one's called the uniform, and we use the notation, I think I pointed out last week, that we use the notation, or we use the term uniformly distributed, but it's not a distribution function, it's actually a density function. And if we say over the range A to B, the height of this would be 1 over B minus A, and I know that because area has to be 1, right? Now, that is about the simplest possible density function that you could have, uniform, and that's one reason we like it. And the other reason we like it is like the resistor example I was doing. When you have no other reason, no reason to believe it's otherwise, you say, all I know it's in this range. So we just use that uniform density to represent that. But now, you know there's a more common one in the real world, and that would be the density that is what? What have you heard? Normal, also known as the Gaussian. How many of you have not seen Gaussian? You've seen Gaussian. You just not going to tell me about it. It may have been a little while. So the Gaussian looks like this. It is the density function fx of x 1 over square root of 2 pi sigma x squared, and we're going to talk about these parameters. E to the negative x minus mu sub x squared over 2 sigma x. And we'll, as I said, we're going to talk about those parameters. It is characterized by mu sub x, which is expected value of x. Y'all are all right if I start throwing that terminology in now, aren't you, even though I haven't defined it? I will define it. This is called the mean or the average value. And sigma sub x squared is the expected value of x minus mu sub x, quantity squared. This is called the variance. You all are familiar with mean and variance, right? And sigma x is the square root of that, would be called the standard deviation. Be called the standard deviation. And if you've taken a probability course, all of you have had EGR 252 here, which is primarily statistics. Statisticians love the standard deviation, but we, other engineers, typically talk in terms of the variance. That one, you know what it looks like, what we call a bell curve. Like that, it's uniform, it is symmetric about zero. It's an even function, except, hold on, don't copy that yet. What I drew there is a Gaussian distributed, but it has a mean of zero. In general, it would not have a mean of zero. So let me draw it in general, like that. Like this, and the center point there is mu sub x, and sigma is a measure of how spread it is about the mean. In other words, low variance would mean it's narrow and very peaked. High variance would mean it's very spread out. Okay? And there's something else here that I want to get into, and this is as good a time as any. You all have had, I know you said you've had a probability course. Most of you have been through some communications where you've done some probability, as well as EGR 252. I want to talk about something a little bit different now, and this is a direction. I said last week there are a lot of directions I could go in. Here's one thing, though, that we need to know. If I were to talk about, let's say, z equals x plus y. Okay, x, y, and z are random variables. Would you agree that if x and y are random variables, then you add them together, you'll get a random variable? But there's something you should know here, and just in case you haven't seen it in other classes, I'm going to cover it here. When you do that, x has a particular density function. Let's say I want to use the uniform because it's easy to work with. Y has a particular density function, right? What about z? It'll have a density function, and I wonder, they must be related in some way, right? If you haven't seen this before, and I suspect you haven't, you're going to be surprised where this leads. It's a very important result. And let's say that f sub x, let's say it's uniformly distributed from -1 to 1. That means this would be 1/2. And let's say y is also uniformly distributed from -1 to 1. In other words, they have the same density function. Okay? Mathematically, so I could say f sub x, f sub y of y. Now, f sub x, just the f sub x means that that's a density for x. F sub y means that's a density for y. But it turns out that they're the same function. Okay? Uniformly distributed from -1 to 1. When you add the two random variables together, you get this result. F sub z of z is f sub x of... Now I'm going to switch over to z. Okay? Can I do that? It's still f sub x. It means the density function for x, but I'm just going to call the variable z. And if I'm going to get a function of z, I need z's on the other side. And the operation is this. Star. What does star mean? And it's not multiplication. What is it? Convolution. You convolve the two. Okay? So here's another use for convolution. Turns out that when you add random numbers together, you convolve their density functions. Now, do you know what it looks like to convolve those two rectangular pulses, boxcar functions? What is it? What does it do? Triangle? Ramps up, ramps back down. So that means f sub z of z would look like this, and it would go, I'm going to claim that it goes from -2 to +2. Yeah?
So the only thing I can't remember, because you will see that in communications, is
Okay.
the amplitude, is it going to be 1 or is it still going to be 1/2?
It's going to be whatever it has to be to make that
Okay.
area 1. And if I take that triangle and flip it over on the other triangle, it looks like it has to be 1/2. But I'm doing that after the fact. 1/2. Okay. Let's talk just for a minute whether that makes sense. And then I've got much, much more to say about it. Does that make sense? What would be if, okay, these two numbers, x and y, they can be between -1 and 1, right? So, how's the only way you could get a number down here close to -2? If both of them turn out to be very close to -1, right? Okay, so they have to both be down there. What about numbers near 0? In what ways could you combine these two to get numbers in here? A number here and a number here, here and there, here and there, here and there. A lot of different ways, right? You see what I'm getting at? And I'll give you a better example. Here, two resistors in series, 1K, 1K, and they're both 5%. What's that going to add up to? Nominally 2K, right? But if both of those could be up to, let's see, that'd be 950 less than R less than 1050. If they're both 1050, it could be up to 2100, correct? Okay, the density function for that series combination, what I'm saying is this, it's 2K, and that's 2100, and this is 950, 1900. Okay, what's the only way you could add those two resistors together and you get a value just very close to 1900 if both of them were very close to 950? What's the only way you could get a resistor close to 2100 if both of them were very close to the upper end, right around 1050? But how could you get numbers around the nominal value? Both of them around the nominal value, or one a little high and one a little low, or vice versa, right? So there's a lot more ways to get those values closer to the nominal value, but notice than there are to get the ones out toward the wings. But notice this, it is possible to get something way down here around 1900 or way up here around 2100. The spread is twice what the spread is there, right? The maximum deviation is 50 ohms. The maximum deviation when you add two together is 100 ohms. Okay, so let's do, if we can do that, we can do something else. And that something else I want to do is, let's add another one of those numbers together. Okay, what would you do? Then let's add another y to that. You would get that plus that and another one of them. So what would you do? Convolve that with that. Right? You don't have to worry. We're not going to get into doing the convolution except just kind of picturing it in our head. What happens when you flip one of them around, slide it through, and you integrate a linear function? What happens when you integrate a linear function? You get a second order, right? You get a quadratic. And so the answer, I'll just tell you, goes something like that. And in that case, it'd go from -3 to +3. How do I know that? If you add three of them together, the smallest they could get is -3, and the biggest they could get is 1, 1, and 1, positive 3. That's a pretty good drawing. What's it look like? It's a quadratic, but what does it kind of start to look like? It's starting to look like a Gaussian, isn't it? You see that? And if it doesn't look like a Gaussian, that's a really good drawing because it's symmetric and it is quadratic. So if you keep doing that, it winds up, if I add this, that, let's just say, I'll use different notation. Z equals x1 plus x2 plus dot 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 plus x sub n. If I'm going to add n of those together, and they all have the same distribution, they all have the same, excuse me, same density function, it turns out that capital F sub z of z tends to become a Gaussian as n gets large, n goes to infinity, regardless of the densities of density of x sub I. Okay? I did it for the uniform because that's real easy to do, and you all can visualize the convolving that. Now, do you notice what I wrote? I wrote that capital F tends to be a Gaussian. Lowercase f looks like a Gaussian, but it's not. Okay? Capital F would be the density function. Lowercase f, it turns out, no, it's not. So that kind of looks Gaussian, and so if I integrate it, it'll look like the integral of that. But the actual density function, turns out mathematically it looks Gaussian, but it's not. But the distribution function will become Gaussian, okay, as n gets real big. Oh, and by the way, notice this says regardless of the density of the x's, meaning I started to say I did it for the uniform case. Doesn't matter. Keep going, and it will still become, even if it were triangular, and you do triangle with triangle with triangle with triangle, it'll tend to be a Gaussian. Tend to look Gaussian after a while. So there's something else here, and if I do this, I'm not gonna give this a name because I'll be honest, I can't remember off the top of my head what it's normally called. But if I were to do this, integral negative infinity to infinity of f sub x of x times e to the negative j omega x dx. Have you ever seen a function like that? I'm sorry, back. E to the positive j omega x. Have you ever seen an integral like that? You better say yes, because that is what? If I'd left that negative in there, what is that function? What is that called?
It's not the convolution.
No, but it's related. Keep going, you're on the right track. You multiply something by a complex exponential and integrate it. What if instead of x I put t? F of t, e to the j omega t dt. What is that? You all know that becomes a function of omega. What's it called? Yeah, come on, you're right there. It is, I'm going to tell you what this one's called. It's called the moment, if I can spell, it's called the moment generating function. What is one of the ways, what is one of the ways we avoided doing convolution? by using the second word is transform. What? This one's Fourier because it's J omega, right? Does that look like a Fourier transform? Turns out it is, except for one thing. We changed the sign on this exponent, which really is just a matter of how you define it. It could be done the other way, but it's commonly done that way. And so that really is pretty much exactly the same as a Fourier transform. And by the way, what I'm about to show you, that's essentially a Fourier transform, but it's called a moment generating function. So instead of doing this convolution in the z domain, what could we do? We could just multiply the moment generating functions, couldn't we? That's the Fourier property for convolution. Convolution in time is multiplication of the Fourier transforms. Come on, you all know this. Okay, so you just multiply those together. And one interesting thing, what if I were, look at this up here, I'm going to ask you to put together all this. What if I were to start off with random numbers that are Gaussian distributed? What does that say? Regardless of the density of the x, that tends to become Gaussian. So what if x and y over here were already Gaussian? What does that say? That when you convolve them together, what will you get back? Gaussian, right. I said it doesn't matter what, I did it for uniform. It doesn't matter what the densities are for x and y, it's going to become Gaussian. Well, what this is saying is, what if you wind up with a Gaussian and then you do another convolution with a boxcar function? Going to still be Gaussian. What if you already got two Gaussians and you convolve them together? So convolve the two and you wind up with another Gaussian. And guess what? Instead of doing the convolution, you could multiply their moment generating functions. The moment generating function of a Gaussian is a Gaussian. Okay? There are only two examples that are known that have the same time function and, I'm jumping back and forth, time function and Fourier transform. And one of them is the Gaussian. It is its own Fourier transform, which means Gaussian there, it's its own moment generating function. Okay, so anyway, I wandered way out there and I didn't mean to digress this much. And I'm not going to pursue any of that. Okay? But I am going to talk about a couple more density functions. We've got the two most important, the uniform and the Gaussian. Another one is the exponential. So the exponential function, density, f sub x of x is alpha e to the negative alpha x u of x, which looks like this. Alpha is where it will start there, and I have to have that alpha out in front in order to make what? What?
What do you mean?
Yeah, you have to make the area 1, right? That is what you said, isn't it? Just
I was
go.
trying to figure out what you were asking.
Oh, okay. Just say sure. Okay. If I don't have the alpha, when you integrate it from 0 to infinity, the area has to turn out to be 1. That's why you have to put the alpha out front. When you integrate this, you get e to the minus alpha x over negative alpha from 0 to infinity. You've got to have an alpha to cancel that out. Make the area 1. Okay, so this turns out to be a very useful model for a lot of things. It's a model, and by it is a model, I mean it's a good model. It's useful for devices for lifetime, LIFETIME, of devices that fail randomly. And what do I mean? Everything to some extent fails randomly. But I'm not talking about things that wear out. Okay? There are certain things, somebody asked me, I was talking about this some years ago, and somebody asked me, could you model like a car engine or something with an exponential model? And my response was, to some extent yes, but overall no, because there are certain things, if you consider the whole car, brakes, belts, things like that that wear out. And that's not a good model for. What it is a good model for, things like light bulbs. Okay? Light bulbs, electronic parts, they can fail at any time, right? Do you ever hear anybody say, I'm going to have to stop using this example soon because we're going to be using LED lights everywhere, and those, the lifetimes on those are 50,000 hours or something. So people are going to be like, no, lights last forever pretty much. But have you ever heard anybody say, I haven't changed the light bulbs in my house recently, so I guess I should go through and change them? You haven't heard that, have you? Why? Do you do that? No, because have you ever had the experience of changing a light bulb and as soon as you flip the switch it blows it? It happens. They can fail at any time. They can, a particular light bulb can last 10 years or it might last a couple of months. Okay? They tend, when I say randomly, what about electronic parts? They might fail at any time. Do you change electronic parts because you say, oh, it's been in there for a while? You change batteries, but batteries run down consistently. It's not a model for things like that. When I say fail randomly, I mean pretty much totally randomly. And one way you might, okay. Let me do a couple of examples here just to show you some conclusions from this. But do y'all see what I mean by just totally random failures as opposed to wear items? Things that get old, that tend to break down with age or break down with wear, right? Your clothes. They don't really fail. They don't wear out at random times. You can say, oh, a pair of blue jeans will last me 5 years. In my case, I think I've probably already gotten 5 or 6 years out of these. But they're wearing. Okay, they're wearing out as you're using them. That's not true with electronic parts, for example. So if I wanted to know what is the probability that a bulb lasts at least 5 years if, let's say alpha is 2. Now, I haven't told you what alpha is yet, but this gives you enough information. If alpha is 2, all I'm really interested in is this. That means this would be 2e to the minus 2x u of x. And so it starts at 2, and it decays monotonically to 0. And alpha is 2. That tells you where it starts, how tall it is at x equals 0, and it tells you how fast it decays. How could I find that? Now this is a density function. This is lowercase fx of x. So to get a probability, what am I doing? What do you have to do to a density to get a probability? You have to integrate. Okay, you have to integrate. Okay, but where would I integrate? Probability, so what I'm wanting is the probability that x is greater than or equal to 5. Okay, and what is it? Where would that be? I'll say 5 is right there. What do you want? Yeah. The area to the right of that? In other words, you want to know what's the probability that x is bigger than 5. That would be that area, okay? Which you could find from integral from 5 to infinity of 2e to the minus 2x dx. And let's just finish it. 2e to the minus 2x over negative 2 from 5 to infinity. 2's cancel and you get infinity, it goes to 0. At 5 you got negative sign cancels out, and the answer is e to the minus 2 times 5? Huh. Okay. All right, yeah. Which is a pretty small number, right? But on the other hand, I don't really care what the answer is. I'm just doing an example here. But I want to show you something else that's very peculiar about this. You all remember conditional probabilities, don't you? Yeah, we done. You know what conditional probability means? It means a statement like this. What is the probability that x is greater than or equal to 7 given that x is always already greater than or equal to 2? So here's my question. The way you would interpret that statement, do y'all remember that now? From some of you were in 435 last semester. We talked about conditional probabilities. The way that would be read is, what is the probability that x is bigger than 7 given that we know that x is bigger than 2? What that would mean in the real world is, this light bulb has been installed for 2 years. What's the probability that it lasts 5 more years, at least 5 more years? Okay? And, excuse me, the definition of that is probability that x greater than or equal to 7 and x is greater than or equal to 2 divided by the probability that x is greater than or equal to 2. Does that sound familiar now? Probability, the way you may have seen it before, A given B is probability of AB over probability of B. And here A is x greater than or equal to 7 and B is x greater than or equal to 2. Right? Okay, so this numerator turns out to be pretty easy. What is it? X greater than or equal to 7 and x greater than or equal to 2. If you do and, you don't need that one. Okay, x greater than or equal to 7 is integral 2e to the minus 2x from 7 to infinity dx. X greater than or equal to 2 is the integral from 2 to infinity of 2e to the minus 2x dx. Okay? In other words, it's already lasted 2 years. What's the probability that it's going to last another 5 years? And I should be able to plug in some numbers here. Let's see, if that one turned out to be e to the minus 10, this one should be e to the negative 14 over e to the negative 4. Do y'all see where that comes from? Or you can just do the integral. It's not difficult. Anybody want to simplify that last answer? Because that last answer is very interesting to me. What is it? E to the negative 10?
It's the same as 5.
Look at that. It's not a coincidence. Same answer. So do you see what I was saying about why you don't change light bulbs just because they've been in service for a while? If I start that light bulb from day one, the probability of it lasting at least 5 years is e to the minus 10. If I say, oh, that bulb's already been in there 2 years, what's the probability it's going to last another 5 years? The same. And by the way, if you said that bulb has already been in for 25 years, what's the probability that it lasts another 5 years? E to the minus 10. Okay? This is sometimes called a renewal process. Excuse me, you see where that would come from? no matter how long it's been in service, it's just like it's brand new. Its probability of lasting any particular amount of time would be absolutely the same, no matter how long it's been in service. And you might interpret that as, if it's already been in service for 25 years and it's still working, we must have got a good bulb. Okay? Because it'll have the same probability as a brand new one. If somebody says, excuse me, want to trade your brand new bulbs for all of them you've got in your house? Well, you could or you could not. It's not going to make any difference. Okay? And that's a fairly good model for things that don't involve wear or aging, that don't fail because of wear or aging. Okay? One last thing, and just kind of a conceptual problem. What is the probability that hold on, give you a different problem, that 1 less than or equal to x less than or equal to 3? Can you tell me right up there, there's a picture, how am I going to find it? How do you get a probability? You integrate. What? And when you integrate, you would integrate 2e to the negative 2x dx, and you need limits on that integral. Where are they? 1 to 3? Okay. 1 to 3. So that means there's 1, there's 3. That's just that area in there. Okay, that's it. Okay? So, now, let's talk about moments. That's enough on just pure random variables. And the reason we talk about moments is moments of random variables. A density function is a complete and total description of a random variable. In other words, if I give you the density function, anything on earth that you would want to know about that random variable, you can figure out from the density function, in theory. Turns out there might be some questions you'd want to know the answer to, but you won't be able to do the calculations. But mathematically, theoretically, we can find answers to anything. But I want to measure things. What if I don't have the the density function itself? And that's where moments come in. We're going to call mu sub x. Moment is also known as expectation. And expected value of x, okay, mean. That one I've already mentioned when we were talking about the Gaussian. Sigma x squared. Expected value, I'm going to take x minus mu sub x, square it, and that's called the variance, as I said before. And that has nothing to do with Gaussians in particular. That's just the standard definition. What do I mean by that? Expected value of x would be integral negative infinity to infinity x times little fx of x dx. Take the density function, multiply with a random variable, and integrate. If you all remember in statics, you all did this. Okay? Y'all remember doing this in statics? Do you remember doing it in Calc 2 probably? Calculating moments. Okay? And what it means is this. Where you did it in statics is you said, okay, I have a beam here, and this beam has a distributed loading. And let's say, you remember drawings like this? And let's say the loading looks like this. Okay, all the way down to here. So it's more heavily loaded on the right-hand end, and say that the beam is of negligible weight itself, and the moment, which is this moment, is what does it mean? It would be the point where you would need to put a, we call this a fulcrum. Remember that? To balance it. I'll send y'all back to calculus. And after that, statics. Okay. That's exactly what you did here. That f sub x, what we're calling a density function for the random variable, that describes that loading. Okay? And the x is just, you measure from out here. And so you weight the density function by the distance, and then when you calculate that, you put in the limits from 0 to whatever the length of the beam is. And when you calculate that, you wind up with a number, and that number represents how far, if we call this 0, how far out you need to put that fulcrum so that the beam will, with its loading, will be balanced. Where its center of mass is, right? Y'all remember center of mass? And then in calculus, you probably calculated a two-dimensional center of mass. You have some kind of a distributed plate, and you want to calculate in the x direction and the y direction where the center of mass is. Okay? In other words, where would I have to put my pen to be able to balance it perfectly? Okay, mathematically we're doing exactly the same thing. Okay? So, in a case like this, let's take that and say that would be integral of x times alpha e to the negative alpha x from 0 to infinity dx. I want to find the mean of that. Can we do it? And I can't believe I've gotten myself into this problem. We're going to have to integrate by parts, aren't we? But you all won't answer any questions about calculus, so we're going to integrate by parts. You remember u equals x, du is dx, dv is e to the negative alpha x, or alpha e to minus alpha x dx. And if you integrate that, v is negative e to the negative alpha x, and the alpha and numerator and denominator cancel. Okay, so the answer is uv negative x e to the negative alpha x from 0 to infinity. Minus integral 0 to infinity of negative e to the negative alpha x dx. First term, at infinity the exponential kills it, and at 0 that linear term kills it, so this term is 0. And cancel the negative signs, and we get e to the negative alpha x over negative alpha from 0 to infinity. And if you plug that in at infinity, it goes to 0, and you get 1 over alpha. Okay? So what does that say? When I did this, the mean of x equals mu sub x equals 1 over alpha. Look over here. Probability that x is greater than or equal to 5, the mean of it is 1/2. So that's 10 times the mean. Are you surprised at such a small number? I hope not, because this is getting pretty small out there. So I want to calculate this. What is the probability that x is greater than or equal to mu sub x here? And you might think the answer is 0.5, but it turns out it is not. Okay? So, Connor, want to ask something? Or?
Is this for the exponential function?
Yes, for the exponent. Yes, it is for that particular function. Right. That would be the probability that x is greater than or equal to 1 over alpha, which would be the integral from 1 over alpha to infinity, alpha e to the negative alpha x dx. alpha e to the negative alpha x over negative alpha from 1 over alpha to infinity. And that gives you e minus 1. 0.368. Very close to that anyway. 0.368. That's interesting. Don't you think that's interesting? When you pick up a package of light bulbs, do y'all ever go to Lowe's and just read on light bulb packages?
Every day. Well, every
Every Saturday. That's about like I am. Yeah, I've spent more time than I really want to admit doing something like that. What does that mean when it's when it says the average lifetime is 2,000 hours? Look at this. Only 37% of them will last that long. Most of them fail within. By most of them, I mean what is left? 63%. 63% of them fail in the first 5,000, I said 2,000 hours, right? Okay, 63% of them will fail before that time. But some of them technically could last infinitely long. Okay? But you kind of know that. Look at the shape of that density function. It's falling. It's tallest at very low values. Okay, so what else are we going to do? Oh, we don't really want to calculate the variance here, but I want to introduce another moment, and that is expected value of x squared, which would be defined as integral negative infinity to infinity x squared fx of x dx. Okay, this is called the mean square. Okay, mean square value. And one of the reasons it's important is for us EEs, mean square actually has a meaning, doesn't it? What about root mean square? That's effective voltage. If you have a random voltage or a random current, the mean square is a measure of how much power is in it. Right? If I take the root mean square, I'm back to effective voltage or effective current. But if I don't take the root, it's just the mean square value, and this is how you measure the power in a random signal. So I will add that as its interpretation. It's the power in a random signal. There's a little bit more to it than that, but that's close enough. And then, if I do this, sigma x squared, expected value x minus mu sub x squared, which is x minus mu x, again, that would be expected value. Okay, I'm going back over here to the definition of the variance and plugging in that formula. What I would have is x squared minus mu x times x minus mu x times x plus mu x squared. Okay, expectation, look at the definition here. Expectation is an integral. Is that a linear operation? Two things that you need to know for it to be linear. If I take the expectation of the sum of two things as the sum of the expectations, what if I said that about an integral? If I integrated f1 plus f2, can I write that as integral f1 plus integral f2? I can. And if I integrate k times f1, can I pull that k out like that? Yeah, if k is constant? Okay, that's proof right there. That integration is linear, and because expectation is an integral, it's linear. So what does it all mean? that is expected value of x squared, minus, mu x is a constant, isn't it?
Yeah.
Mu x is that. We've integrated the density function, we've integrated the randomness away, and so that is 2 mu x times expected value of x. And the last one is just mu x squared. But what is expected value of x? Yeah, expected value of x. Does it have a name? Mu. Okay, mu x. So this is expected value of x squared minus mu x squared. Okay, so you have to be careful when you read this formula. The variance is the mean square minus the square of the mean. And I said it properly there. Be careful. The mean square is expected value of x squared. The square of the mean is mu squared. Okay, got to be real careful how you say that. That's the way we normally calculate it. It's a lot easier than actually going through and in here putting x minus mu x squared. Okay, that's a pain. Okay, we'll be done for today.